Hi everyone. All right. um, yeah, just to make some announcements. So again, final is on the 19th, 2 slots. It will mostly cover 1 to 12, 95%, and then 13, 14. So if you're not comfortable with this, you should devote the next 2 weeks only on the 1 to 12. Do not try to do the 13, 14 if you're not comfortable with this material, please. Okay, what else? As usual, we have office hour Fridays, 3 to 4 and 9 to 10. So today we're going to talk about Hausdorff metric. And fixed point. So, okay, I see a question. What's the question? Only 1 hour for final. What? What are you talking about? What did I say 1 hour? Oh, sorry. I don't know what I said. I'm sorry. I apologize. I was writing my office hours. Okay, thank you. That's funny. Most of metric and okay. All right, so just very quickly, what was a metric? So it satisfied positive definite. It satisfied symmetry. And it satisfied triangle inequality. So today we're mostly going to talk about Hausdorff metric. I'm mostly going to go over 11.1 and 11.7. So if you want to follow what we're doing, just go to these chapters. All right. So Hausdorff metric. So this is a metric over compact sets. In Rn. Okay, so what is it? DH of AB is the maximum. Actually, I want to write a little bit different. So sup A in A, the distance from A to B, maximum sup B in B of the distance of B to A. All right, so let me just draw a picture. So if dH of AB is epsilon, we have the following thing. So this is A, and then B, might not contain A. So this is B. But when you have this statement, okay, let me draw it again. So this is A. And then it says that A is within, let me do it with dots. A is within B epsilon. And the same in reverse. So, how do you say it? I will define what these are. Okay, so what are we talking about? S epsilon is defined as the following set. How do you say it? I want to write this carefully. I know. So y is in B epsilon x, where x is in S. Good. So what does that mean? Let's do a simple example. Suppose S is a line, then S epsilon, you take this line and you put epsilon ball. Actually, sorry, 1 second. Let me make it smaller. Let me take it to be this interval. Then this guy is S epsilon. So this is AB. This hits at A minus epsilon, B plus epsilon, like that. Okay. Okay. Let's prove that this is a metric. So suppose that dH of AB is 0. Okay, so that means that sup, A in A of the distance, A in B is 0. So, distance of A to B for all A in A is 0. So A is in B because, actually I should define what distance is. Nobody asked. So I should say it because I don't think you know what do we mean by distance. Yeah, people don't always care. Okay, so this is the infimum B in B of A minus B. So this is B, and this is A. This guy is the distance. You find the closest point. All right? Everybody happy? Everybody's here? I see a question. So if the distance is 0, then we have that I just said what the distance is. That's hilarious. Are you people like watching some Netflix show or something? I don't know. Like, it's the exact same thing. It's like identical. So infimum of A in A of A minus B. Yeah, the distance is symmetric, so it doesn't matter. All right. So A is in B, and so why is that? Yeah, so why does this imply this? Let's see. So it says that the infimum of B in B of A minus B is 0. Okay, so it says that, you know, the distance to the closest point is 0. But B is compact. So this distance is attained. So you get this is equal to A minus B sub A. And so you get A is equal to B sub A. So this is by the extreme value theorem. So it's tricky. So the reason we have A is in B, let me repeat, is because when you say the distance is 0, you're saying that the infimum is 0, but the infimum is attained. So let me, too much noise here. So, but B is compact, so infimum is attained. And so you get BA. Okay. I see a question. So distance, no, that's not what I said. I didn't say that they're the same. But that's a good question. So let me find an example. That's actually a very good question. No, that's not what I said. I didn't say that they're equal. I said that the formula is symmetric. You say equal, I said symmetric. So, so right here you can see, first of all, you wrote little a and little b. So these are two different things. Okay, so let me give you a counterexample. Let's see. So take A to be 2 points and take B to be 2 other points. Then this is A1, A2, B1, B2. Distance of A1 to B is this guy. And then distance of A to B2 is this guy. The thing is that guy here. And the R is not S. right? Okay. Good. I see we're 11:25. I doubt we'll do anything. That's all right. Okay, so fine. Let me prove it's a metric. So we proved, yeah, so A is in B for all A in A. So you get A is B. You get A is a subset of B. And reversing roles of AB, we get B is subset A. So together we get A is B. All right. Symmetry is obvious. I'm not going to do that. So let me do, what's the other one? Triangle. So, right, you have A, B, C. Okay, so we have DH of, what is it, AC. And let's study the distance of arbitrary A to C. Okay, fine. So, yeah. Again, by compactness, so let me say it like this. Fix A in A. By compactness, you can find some guy BA that is closest to A, and you can find some CA that is closest to A. Okay, so now the distance, this is less than A minus CA. I mean, it's equality, but it doesn't matter. Then you use triangle. No, that's not what I wanted. Sorry. Right, so, and then from this BA, you find the closest point in C. Call it CAB. Okay, now that's right. So you have A minus CAB. Yes. And then this is less than A minus BA plus BA minus CAB. And this guy, we set it to be equal to the distance. You know, what am I saying? Yeah, this is the distance A to B. And this is the distance of BA to C. Okay. Call this 1, call this 2. Right, and then you can do it. This is just the DH of AB, because you're taking a soup over A in A, and soup over B in B. All right, and that's the triangle. Okay. All right. Now let's go to the meat. Where am I? Yeah, at least I want to get completeness maybe I'll continue next week. We'll see. Okay, so I want to do first a simple example, and maybe I'll leave the details to you. Yeah, let me just write. So if A is A1, A2, and B is B1, B2, like that. Then you can find that the Hausdorff distance of A to B is the following maximum. So it's A1 minus B1 and A2 minus B2. So so I say a few words. Yeah, let me say a few words. So this is, how do we get this? So you have sup A in A minus B, and B in B, A minus B. The closest guy, the furthest guy from B is A1. Okay, let me say it differently. So first we have an infimum. Let me like open this up. It is too confusing. So max sup A in A, inf B in B, A minus B, sup B in A, B, infimum A in A minus B. So note, we cannot swap inf and sup. What A is closest to B? Well, that's just B1. What point of A is closest to B? That's A2. And then what point is further away from B1? That's A1. See? B2. Okay? You have questions, just tell me. All right. Yes, fixed point. Now we're going to talk about the fixed point. Fixed point and Hausdorff distance. Okay. In many applications, the data sets are not graphs of functions. So here's an example from data imaging. I hope I can give you the picture. That's fine. I'll just, oh yeah, I'll give you this. Let me draw it. So this is one image. Okay. Can I make it bigger? Yes. So this is from an actual application. I draw on the picture. Oh, that's cool. So here's an application of Hausdorff imaging. So you want to find this snippet inside a bigger image. I can't emphasize enough how big this is in applications. You know, like detecting cancer, detecting, you know, all kinds of things require you to have good metrics to do that. So if you want to learn more, see what is called modified Hausdorff image. And it's used all over the place, from astronomy to neural networks. Okay, so, right. So what they do is they call this set A, and how do you say it? And I don't want to go too into it, but what you do is you partition, so call this B, partition image B, and into a union of BI, so you split the image, and then compute the Hausdorff distance of A to BI. So minimize this guy over I and find the closest, closest the BI star to A. So that's like the main idea. So here you don't have graphs of functions. Yeah, so one question is, why does this even converge? Why does the algorithm converge? Okay. All right, so yeah, why does the algorithm converge? So now we're going to chapter 11.7 and to see why, what properties we have for this Hausdorff metric. Okay, so what's the theorem name? Let me see. So this is 11.7.2. So this is a tricky proof. I'll try to do it justice. See a question. What's the question? Do we have, no, they don't have to be disjoint. King Yang is right. I draw them disjoint because the pictures are nicer. Right. So one thing you need for convergence is completeness. So how do you say it? The metric space compact sets in Rn, comma, with the Hausdorff distance is complete. In what we've been talking about all these months. So so what do we mean? We mean that let, what's the notation? AN. Let AN be a Cauchy sequence. What does that mean? You know, fix epsilon. There exists an epsilon so that the Hausdorff distance of AM is less than epsilon. I hope I can at least do completeness for you. Okay. All right. Fine. Okay, so you have this claim. Let A be the following set. So we take their intersection and union. Think of it as what is it? Lim sup. Then distance of I think this is like lim sup. I don't quite remember now. I think this is lim sup. Yes. Then AN A goes to 0. That's what we will prove. All right. So we'll show that that this guy A is compact, and you have this Cauchy sequence converging to it. So AN converges in the space. All right. Okay, all right. So, okay, what's my first step? I wanted to do Sierpinski triangle too. I don't think we'll have time. Maybe on Tuesday. Okay, so as usual, fix epsilon positive. Want to find n epsilon so that for all n bigger than this n epsilon, I don't like this n epsilon, it will confuse you. So I want to find an n so that for all big N, the distance to A is less than epsilon. All right. Yeah. Right. All right. So first, A is inside AN over epsilon. Let's prove that. If I prove the other one, we're done. So first I prove this and then the converse. Yeah, okay. So by Cauchy, for ij bigger than n, what do you have? You have, you know, dh of ai, aj is less than, what is it? Less than epsilon. Sure. So again, you can take one of them to be n. Okay, that's fine. So that gives you ai is within an epsilon for all I bigger than n. Okay. So that says that, what is it? Where am I? Yeah, so remember, A was the intersection, K bigger than 1, I bigger than K. What is it, AI? Here. Yeah, so you get this guy. Right. But this is inside. Yeah. So what do I want to say? Right. Yes. Yes. Let me do one thing. So for all I n, it's inside. So the union I bigger than n is in this guy. So you know, A is the intersection of these guys. Which is inside the union I bigger than n. Okay, now we got it. Which is inside A and epsilon. All right. Hopefully, some people are following. So, again, we want to show that this limit exists, and we work one at a time. So we show this first, and then next we'll show the reverse, meaning AN is inside A of epsilon. So if you have both will give that the distance of AN to A is less than epsilon. Okay, and that would be the end of it. Okay, I don't know how you guys are following. It's very complicated. Okay. What was my next step? Okay. So let me do it carefully. Yes. So fix AI in AI. I see a question. Could you explain how A is a subset of the union? Sure. So this is the intersection, right? Actually, let me do it on the left, on the right. So this is a more general set theoretic thing. In general, when you have, you know, B1 intersect B2, intersect B3, you know, this is inside B3. So here we have, you know, union I bigger than 1, intersect, blah, 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 I bigger than n, intersect, I bigger than n plus 1, so on. But same logic, this would be inside the union of I to n. Is that okay? Okay. Fine. So now, let me not write this. Let me write more carefully what we're doing. So now we're going to show So now we're going to show that AI goes to A. So what we'll do is we'll fix AI in AI, and we will find A in A, so that AI minus A is less than epsilon. Okay. So let me write it like here. Okay, I have some time, so let me repeat what we're doing. So I'm following the notation from the book to keep it clean. Let me call this I, like in the book. All right. Again, we fix epsilon, and we want to find n big enough so that the tail converges to A. This statement here is equivalent to the following. AI is within A of epsilon, and A is within AI of epsilon. Okay, so if you want to have Hausdorff distance to be small, you have to prove both of these facts. And both. Ugh, all right. So we prove the first inclusion, that A is inside AI of epsilon. Right? And that. And now we prove the reverse inclusion, that AI is within A of epsilon. Okay, so if you prove both, you get Hausdorff distance. So how are we going to do this? We're going to take an arbitrary point from AI, and we're going to find the closest point A. So this is the, how do you say it? So let me write it here. So distance of AI to A is less than AI minus A, because this is an infimum, which is less than epsilon. But this was true for all, for all AI. So you get dH of AIA is less than the sup, and this is less than epsilon. All right. So I have to prove you this claim right here. Okay. By Cauchy, AI is within AJ epsilon for all j bigger than n. In fact, even I. Let me just write I. So you have that. Good. Then for each j, there exists an AJ that is close to AI by epsilon. So again, let me draw some pictures so people don't get lost. So this is AI, and this is you know, AJ epsilon, and this is AJ. And it says that there exists at least one guy, AJ, that's close to AI by epsilon. All right. But this guy is inside AN, which is compact. So by Bolzano-Weierstrass, you have subsequential sequence. Going to A in here. So now we want to show that in fact A is inside that in fact A is inside our limit point A. So we have AJ is inside AI, which is inside the union, AM bigger than I. Yeah, so we have that. So how do you say this? Do I want to say this? I'll just say this, AJ. Okay, so A, right, so A is inside the union of, how do you say it? Of the limit point. So take J bigger than 1, and then UMJ AM, right? So each of the points is inside, all AM, AJ to infinity. So by limiting, A is inside the intersection. But this is just A. So we're done for today. Let me go over the proof. So here we're proving completeness, and this is important because you want to know that your space has limits, contains its limits. So remark, we need this for algorithms, for numerical algorithms involving a Hausdorff distance. We need to know that there is a limiting object. See discussion with dotted number. It's the same problem. see above discussion. So we have all these fancy imaging algorithms, and we need to know that they have a limiting object to approximate. So we prove that mathematically there is something to approximate.